Now I'm going to begin talking about introducing us to statistics. Basically, here I want to lay the groundwork for understanding certain notations and structure that help us understand essentially the language of statistics. If you just remember a few key bits of notation and some key organization, it'll essentially allow you to unlock your understanding of all the equations we'll be encountering throughout the semester. So this will hopefully seem pretty basic, but it's the sort of information where if you retain it now going forward, it'll be extremely helpful and relevant each analysis that we do. So in order to start talking about understanding how to approach the language of statistics, first I want to touch on what exactly statistics is. So your book defines statistics as a set of tools and techniques that is used for describing, organizing, and interpreting information or data. Really, in that this is a statistics class, we're going to be living within that data analysis stage of the theory data cycle. We're living at a particular part of that cycle where we're essentially trying to figure out what the best approach for analysis is to let the data tell us a story. You could think of any statistical analysis as like a tool in your tool belt. For different kinds of data and different kinds of research questions, there will be a statistical analysis that works to help you let the data communicate something. More generally, you could think of this as a way to understand the world. It's a certain tool that exists within the realm of psychological science. It's essentially a tool that lets us let the data speak for itself as opposed to just putting our understanding of it first before we actually crunch any numbers. So, really basic approaches where statistics can help tell a story. You could just compute an average, a mean, median, or mode. This will tell you something about the variable that you're interested in. Let's say average salary of psychology graduates. This is going to give you something of like a central tendency to sort of ground your understanding of where the average score is. So a statistic as simple as an average sort of lets you understand something more about the variable you're interested in. You might be interested in distribution of scores. You might wonder whether or not on a particular exam, if all of the scores were clustered very close together or if there was a massive spread. Both of those two possibilities tells you something about what was going on with exam scores. Once you get a little bit further in learning about different analyses, it's going to be about linking distinct variables together. So let's say the strength of the relationship between smoking and lung cancer. These are two variables, smoking and lung cancer. The idea is we want to link them together to sort of tell a story. The nature of the question that you ask and the nature of the sort of research claim that you're trying to make is going to determine what statistical analysis is appropriate. When are you merely computing an average versus how are you going to quantify strength of the relationship? It's going to depend on basically the way you collect your data and the sorts of variables that you are assessing. So, for example, you might look at a statement like strength of the relationship between smoking and lung cancer. The idea is to think to yourself, I know what analysis is used for that. I know that that's going to be a correlation, and I can interpret the statistic itself. Okay, so this is something to keep in mind whenever you're reading something describing statistical results. Look for the language of the statement and what it tells you about what sort of analysis might have been used in that particular bit of data analysis. Two general classes of statistics exist in the sort of framework of statistics we're using here. It's what we refer to as Fisherian statistics. There are other approaches to statistics. We're just learning this one. The Fisherian statistics fall under two general classes, descriptive and inferential. You basically start descriptive, and this is when you're trying to describe or summarize something about a single variable. An inferential statistic is going to be that next step, linking variables together to understand how various constructs interplay with each other. Okay, like I said, descriptive statistics are more so to just summarize, again, merely describe the data you have in front of you. So the idea is you collect some data and you want to, in some way, synthesize or summarize what's going on there. So if, let's say, you have a tiny little data set where you just polled 6 people on their major and their exam grade, how would you go about describing what's going on there? Well, the story you tell about major is probably a bit different than the story you would tell about exam grade. You might look through the major variable and say, well, looks like the most common major is psychology, right? The most frequently occurring score, that summarizes and tells you something about the data. It takes all of that information and it kind of condenses it down in a way. Some information is lost by just saying which is the one most frequently occurring score, but it still, in some way, pares down the data from all 6 of those scores and it summarizes it. Now, if you look over at exam grade, you'd probably think, well, I don't necessarily want to identify the most commonly occurring score. All those scores look different. Well, since those are quantitative values, you might think to yourself, can't I just take an average? Yes, exactly. That's just a different approach for summarizing what's going on with all of those various scores. So again, this is an exercise to demonstrate that depending on the kind of data you have, you'll have different approaches for what is the best strategy to summarize and describe your data. Inferential statistics, like I said, it's the next step. It's once you've summarized and described what's going on within each of your variables individually, your inferential test is going to be when you want to make some broader interpretations and draw some conclusions. This is going to come into play later after we learn about what we call hypothesis testing. If you know about p-values and statistical significance, there's a whole theoretical structure that supports our ability to do that, and that's what sets your inferential statistics apart from descriptive statistics. So this is going to be any of your more advanced statistical analysis, be it a Pearson's R correlation coefficient, be it an analysis of variance to look at group differences. Depending on the research design that you have, you'll be opened up in your inferential statistics to either make association type claims, that is to say link variables together, or depending on the strength of your research design, you might even be able to make your causal claims, that one variable caused changes to the next. Again, I encourage you, if you ever are reading about research, or if you're reading a research question or a research design or some results, think about how the language that you read reflects different sorts of claims and different sorts of analyses, right? So if the research question is if there's a relationship between exercise and happiness, that sounds like it's going to be more correlational. In terms of trying to evaluate causal claims, this is going to be a slightly more intense sort of a research design. The language for each kind of a claim is distinct, and so I would just encourage you to keep an eye on these research questions and research claims to figure out what sort of language is at play there. But again, these inferential statistics are a bit more advanced. We need to build up our knowledge of descriptive statistics first because those undergird our ability to do our inferential tests. So like I said, I want to lay a framework for a common language that we're going to use to talk about statistics. Essentially, what I'm trying to do here is I want to unlock your ability to read statistical equations. You might think to yourself, I know what numbers mean. This is not that. It's about reading the symbols that allow you to take an equation and apply it to any actual set of data and churn out an analysis. The idea of having a language of notation that we'll do our statistics with is essentially a way to make sure that one person using the equation will come to the same exact numerical result as the second person. In order to do that, we need to have a shared notation and we need to have a shared syntax for how the notation works. I compare this to language because, in a sense, it is a kind of language. Whenever you share a language, the idea is it's a shared system of communication that lets us have common ideas about certain meanings. The reason I think statistics applies to this sort of a structure is that you need to have a shared notation, right? The word for one thing needs to be consistent person to person if you're speaking the same language, or else people are going to get confused. So you need to have a shared system of symbols. Additionally, language is predicated on certain syntax or grammar rules. The idea that in different languages, the verb occurs somewhere systematically in the sentence, and that's your indication that that's the verb versus something else. Essentially, there's a certain organizational structure or syntax such that you know where the notation belongs in a certain equation. Okay, so I'm going to walk through the notation and then I'm going to walk through this quote unquote syntax. And by the end, hopefully you will have basically most of the tools that you'll need to read all of the equations you'll be encountering this semester. Okay, so there's notation differences that set apart what we call a statistic, not statistics as in what we're doing here. A statistic as in the statistic on how many people have depression in a certain sample. So a statistic, as opposed to quote unquote statistics, is a single value measured from a sample. So you sample a series of individuals, let's say in the Miami Psychology Department, and you assess what is the most common, let's say, what is the average income? Like, let's say you poll a bunch of psychology students in the psych department on their income. You collect all that data. That's your sample data. Your statistic would be computing the actual average income based on that information. If you see notation using Roman letters, basically all the normal letters that you see in the English language, that indicates that you are looking at a numerical statistic, essentially a value that's used to summarize information from a small sample. So whenever you see variable x or variable y, this is essentially the system of notation. So x is meant to stand in for any hypothetical score within a given sample. Okay, so you would have variable x, and x could refer to any single score within the sample. If you see x bar, you see x with that line above it, we call that x bar. That is an indication to take the mean of the sample. So whatever variable is currently being defined as x, if you see x bar, you're being directed to take the mean of all of those values. You might see some Greek notation tossed about in equations, not as often as the statistic notations, but basically anytime you see a Greek letter notation as opposed to Roman, you're dealing with a summary value that applies to what we call a parameter. So as opposed to sampling, which is when you are only taking information from a small group, from an entire population. A parameter is when you have information that sums up everyone in the population, so maybe some census data, for example. The reason you're not going to see Greek lettering quite as often is that it's not typically going to be the case that you can take information from everyone in a population. If you're interested in the psychology of people generally, right, you can't poll everyone in the world to get an accurate idea of what's going on with that variable. That's why we're so often dealing with samples as opposed to entire populations. But it is at times possible to get information from an entire population. If this is what you have, then that is not called a statistic, it's actually called a parameter. And it would be summed up or communicated with, again, a Greek letter. Mu specifically is going to be the notation that indicates that you have a parameter of the mean level of the variable for an entire population. So this is your x bar, essentially, but applied to a population in its entirety. Like I mentioned, you're not going to be dealing with data analysis that is looking at an entire population most of the time. Most of the time in statistics, we're stuck sampling because that's going to be basically who we can get our hands on in terms of actually running the data. You might be thinking that talking about sampling is more so the realm of research methods class, and that's true, but I think it is important to understand the relevance of sampling strategies to understanding statistics. Essentially, what we're trying to do anytime we do an analysis on a sample is we're often trying to make assumptions about the population more generally. The way we do this is with a two-pronged approach where we try and have our sample taken in a way that is as representative of the population as possible, maybe through random selection. And we additionally want to use as rigorous a statistical process as we can. So for example, by testing for statistical significance. The idea is that by using as representative a sampling as we can and using the best statistical procedure we can, we are basically hoping that our analyses approximate as close as possible what is actually true about the population. Why we gotta be mowing the grass all day, man? I swear to God, they come here every day. The grass doesn't grow that fast. I am sorry if that's loud and annoying, but I can't do anything about it. All right, moving on to some more notation and terminology. Like I said, X is going to basically just be a shorthand for whatever variable you're currently contemplating. So your variable X, maybe it's score on a quiz or something. You would have your variable, and then you would have your actual specific values from the sampling, the data that you actually collected. If you were to see X with a subscript notation like that, when I say subscript, you see how that I is sort of a half line down from that X? That's what we call a subscript. If you see that, that's calling your attention to any individual score within the sample. So X refers to whatever variable is currently being defined as X, and the I calls out whichever specific score in the data set you need to look at. So for example, if you were to see X sub 4, that would be directing your attention to the fourth score in that column. So X sub 4 is 7. You're going to see these subscript notations sometimes, not altogether that common, because usually we don't care about single scores within the sample. We care about all of the scores together. But if you ever do see that notation, that's what it indicates. Okay, you might be familiar with the sigma notation. You likely learned about it in statistics, so this is hopefully a refresher. If you see a sigma ahead of your variable notation, that is a directive to sum up all of the scores in the sample of the variable currently defined as X. So sigma X in this case is directing you to add up all of those values in that column. So sigma X just equals 62, because that sigma ahead of the X is a command to do a certain mathematical function. So if you see sigma X, sum up all of those scores in that column. Now you might see something like this. You actually have two commands present within this sigma X squared. You want to be really careful here, because here's where it starts to get tricky. Looking at that single term, you have two things that you need to accomplish, a squaring and a summing. The question is, what do you do first? You might be inclined to think, oh, do I just square that 62 I got in the previous slide? And that's no, that is wrong. That is not actually what you do here. And you have to pay attention here, because if you inadvertently do this the wrong way, your values are going to be way off. So what is sigma X squared actually asking me to do? Sigma X squared would have you square each score individually, so square of 13, square 9, square of 15, etc., then sum up all of those squared values. The order here is very important. If you did this the opposite way, your value would be off. So what you need to do here, if you see a notation that looks like this, square every single score of the variable X first, then sum them up. So sigma X squared equals 688. Again, notice that 13 was squared, 9 was squared, 15 was squared, and then I summed up second. Okay, so again, if I was to do this in the opposite order, where I just squared the sum of X, this would be a way different value. So be careful to keep an eye on when you see something like this, because that is in contrast to what you see here. The addition of the parentheses changes sort of the syntax entirely. This is completely reordering what you're supposed to be doing. The addition of the parentheses is an indication that the sum of X is prioritized over the squaring. So this would be the command that actually does have me squaring that sum of X value that we got 2 slides ago. See how different that value is from the one on the slide just before this? That parentheses changed the value that we get from 3,844 from 688. Obviously, if you do this when you were supposed to do this, imagine just how off your numerical calculations are going to be. It's a simple distinction, but you have to, if you don't see parentheses, make sure you square first, then sum. I'm belaboring the point because trust me when I say this continues to be the number one thing that students screw up on in doing calculations on exams, is neglecting to square before they do a summing. This crops up time and time again. So trust me when I tell you, I think it's worth it to really drive this point home, that you need to read your equations carefully, because the distinctions that I'm pointing out here can really mean a lot for accurately calculating your analysis. Okay? You're thinking to yourself, how did I know that the parentheses changed things so drastically? Yeah, I'm bringing it back to some classic order of operations. That's it. I've been building up to this point because I kept saying, syntax and grammar and structure. Think about it this way. In order to have a sentence that you speak be in the proper grammar and structure, you need to make sure that the words come out in the specific order, right? In syntax, basically, it's a way where you can make sure that language clearly communicates a specific meaning so that whoever you're talking to doesn't get confused. The idea of having words that we use means something consistent person to person, and having a syntax that's consistent person to person will ensure that when we're talking to each other, the points don't get lost and we don't get confused. This is what I mean by the language of statistics. If you have the notation down, you essentially have the words. If you have the order of operations down, you essentially have the syntax. Those two things together are going to make it so that you can read any equation I show you, from the most simple to the most advanced later in the semester. The language is the same. It's just being able to retain the notation and remembering to look carefully at any equation and thinking of it like a sentence, right? With a particular structure and syntax governed by the order of operations and specific notation that's meant to direct you to different variables. It's as easy as that. Okay? You might remember, please excuse my dear Aunt Sally, if you need to revisit that to remember the order of operations. Why not? There's a reason why they like to have these kicky little acronyms. It helps us remember things. You might be thinking to yourself that the order of operations is second nature. You don't need to remember it. Again, I repeat that simple failures to do things in the ordained order of operations accounts for the vast majority of messed up calculations that loses points on examples throughout the semester. Okay? So forgetting to square things first before summing, again, that difference between 688 and 3,000 something, imagine how much that's going to screw up your calculation. So trust me when I say it seems simple, but I really want you to understand that any equation you see from here on out, all you have to do to be able to figure out what it's telling you to do is the notation and the order of operations. Okay? And again, I'm going to give you equations on all your exams. You don't have to memorize them. You just need to be able to read them. As a little recap, right, again, you might see a subscript notation directing you to a specific score within a data set. You'll see the sigma notation a lot. You're going to see that crop up a lot. That's an indication to sum up a series of scores. If you see a bar over a variable name, that's an indication to take the mean. Okay, so if it's a variable x that you're currently looking at, you're going to see x bar. You're eventually going to see y bar as well, because once we're dealing with, let's say, correlating variables together, you're going to have variable x correlating it to variable y. So anytime you see a variable notation with a bar over it, you need to take the mean. Okay, and then this distinction here, again, trust me, this is going to come up again and again and again. If you see a notation like this, sigma x squared, make sure you square first, then add. If, though, you see those parentheses, you know that the order of operations has parentheses ahead of exponents. So in that case, you take that sigma x, that 62, and you just square it. Again, look at the difference between those two numerical outcomes. And again, keep in mind that if you can just keep that straight, right, what the absence or presence of parentheses or exponents or any of that does for the equation that you're computing, you're going to unlock all the keys to the kingdom. You're going to get A's on all the exams. We're all going to have a great time. All right, that'll do it for this round. I hope you guys are doing well. I'll talk to you soon.